Good morning, everybody. Continuing our last video with practicing Mad Spam. Hopefully you've had a chance to try these problems down at the bottom. So I'm going to go ahead and go through these. We've got 4 to the 5th times 4 to the negative 3. So we identify our base operation, which is multiplication. So this is the m to the a part of Mad Spam. So since we are multiplying, we add those exponents together. So 4 squared, which we are going to simplify to be 16. On the next one, this one I would put a star by. It's a little bit tricky because this isn't negative 3 squared. It's 3 squared and then the opposite of it. So using PEMDAS, we have to evaluate the exponent before we switch the sign or do the subtraction. So this one would be negative 9, whereas the one right next to it says negative 3 squared. So this expansion would be negative 3 times negative 3, which would be a positive 9. And I would put a star by this one as well, because mixing those two up is something that I see a lot in Algebra 2. On the next one, now this is where we start getting into some of the monomial business that I talked about in the last video. So first, we've got negative 2x squared, which we could do as negative 2x times negative 2x, but using our power rules, we have parentheses, so we are powering up. Now, how many powers do I have in this parenthesis? 2 has a power of 1, and x has a power of 1. So when we power up, we are going to multiply both of those exponents by 2. So one monomial, but 2 different powers, one for each of its parts. So this turns into negative 2 squared and x squared. Notice that I'm leaving that negative 2 in parentheses because it was in parentheses originally. So this simplifies to be 4x squared. For this next one, again, following PEMDAS and looking at our power rules, we've got parentheses, which means we are powering up. How many exponents do I have in that parenthesis? We've got a power of 1 with the 1, a power of 1 with the x. So when I power up, we multiply those exponents, which gives me 1 to the 6, x to the 6. And what is 1 to the 6? Just 1. And x to the 6 is x to the 6. So this is negative x to the 6th. All right, moving on to number 6 down at the bottom. So in this one, if I approach this from a PEMDAS standpoint, is there any simplifying that we can do inside that parentheses? Nope, can't do anything with 3/4. I can't simplify anything with the x. So next we move to the powering up part. Now here's the tricky part. How many exponents do I actually have inside this parentheses that are going to get powered up by 2? The 3 has a power of 1. The 4 has a power of 1, and the x has a power of 1. So there's actually 3 different exponents I'm going to distribute that power of 2 to. When you are multiplying the powers, remember you're multiplying the exponents by 2 and not the bases. So sometimes students will say that this top part is 6, but it's not 3 that's getting multiplied by 2. It's 3's power of 1 that gets multiplied by 2, which gives me 3 squared, which is 9. 4 to the first raised to the power of 2 gives me 4 squared, or 16. And then x squared stays x squared. Now, sometimes students look at this and they say, can't I, simplify that? Our brain kind of tricks us here because, yes, 9 and 16 are both perfect squares, but I can't just square root like I'm the god of math. I can't just square root one side of an expression. So you can't take a GCF out of 9 and 16. So this is actually our simplified answer. So don't try to just square root wherever you want. On this next one, as I'm looking at these, we see that we have a few different exponent operations between the bases. We've got multiplication, 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 division, multiplication, and we also have a negative exponent. Now, my strategy is anytime I see a negative exponent, I typically resolve that first. And usually I do this first, especially, when the problem is dealing with division. So I'm going to go ahead and resolve that negative exponent first. That's going to give me 12d to the 5th, d squared, f times, when I send him upstairs to lose the attitude, it becomes f to the positive 1. And then all over 3. So now I can start simplifying my like terms, if you will. So if I look at 12 over 3, yes, these are separated by division, but I'm not going to subtract anything because, again, that is an exponent rule. So how I'm going to approach 12 thirds is to simplify it like a fraction. 12 divided by 3 is 4. Now with my d's, they are separated by multiplication. So using the m to the a part of MathSpam, we are going to add those exponents, which gives me d to the 7th. My f's are also joined by multiplication, so I'm going to add those exponents. Now, if it helps you, you can go ahead and throw in that implied power of 1 with that first f. So 1 plus 1 gives us f squared. Now, what if we hadn't resolved that negative exponent first? I could still work with the problem this way. I would have just had f to the first and then minus a negative 1. So because these f's are separated by division, I would subtract those exponents. So 1 minus a negative 1. Now, as we remember from doing polynomial long division, sometimes double negatives can trip us up. So though you can do it this way and you will still get 1 plus 1 or 2, it is my recommendation when you are dealing with division to try to resolve those negative exponents first. All right, let's go ahead and take a look at the next one. On number 8, is this a foiling problem? Poignant pause. Sometimes students will be like, oh yeah, it is foiling because I'm going to take 6 times a 4 and then 6 times the g. Folks, this actually isn't a foiling problem because foiling is for a binomial times a binomial. This is a monomial times a monomial. So if it helps you, we can think that all of these terms are actually joined by multiplication. So when I go to simplify this, we're kind of using that commutative property and just rearranging our terms. I can put the 6 and the 4 together, the g to the 5th, and the g together, and then I can simplify kind of my like units. So 6 times 4 is 24. G to the 5th times g to the 1st. These are separated by multiplication, so my base operation is multiplying, so we add the exponents, so g to the 6th. Alrighty, on number 9. So from a PEMDAS standpoint, if I start inside this parenthesis, oops, sorry about that. If we start inside the parenthesis, is there anything that we can simplify? We've got 5xy to the negative 4th. Now, unlike in this problem where I said, hey, why don't we go ahead and resolve that negative from the beginning? Because there's no division here, so no chance of double negatives, we're actually going to leave that y to the negative 4th alone right now. So we're going to let him have a bad attitude, and we will take care of resolving that before the end of the problem. Now, z to the 0, anybody remember from the last video what anything to the 0 power is? It is 1. So the 0 exponent property, anything to the 0 power is 1. So z is equal to 1. So 5xy to the negative 4th times 1 would just give us 5xy to the negative 4th. And then raised to the 3rd. So identifying our base operation, we are powering up. We've got those parentheses. So that means we are going to be multiplying the exponents by 3. So how many exponents do I have in that parenthesis? We've got 1, y has negative 4, 2, x has 1, and 3, the 5 has a 1. So every single power in that parenthesis is going to get multiplied by that exponent of 3. So this turns into 5 cubed, x cubed, and y to the negative 12th. And remember, folks, 5 cubed is not 15. It's 5 times 5 times 5, or 125. And then x cubed. Now, y to the negative 12th, what we are going to do with this bad attitude is send him to the downstairs of this fraction. So we could turn this into a fraction by putting it all over 1. So to resolve that bad attitude, we are going to send him to the downstairs where it becomes y to the positive 12. And that's how we know our expression is simplified, because there should be no more mad spam operations that we can simplify. So no same bases, no negative exponents, no fractions that we can simplify as well. So on this last problem, we've got 1x to the 6th, so 1x times itself 6 times. We've got 2 different powers in the parentheses, so when I power up, that 6 is going to go to both of those exponents of 1. So negative 1 to the 6th, x to the 6th. 1 times 1 times 1 times 1 times 1 times 1. Hopefully I did that 6 times is 1. And that gives us negative 1x to the 6th, or just negative x to the 6th. Oh, and you know what? Forgot, I actually changed this problem, because as you may have noticed, it is the same as the one directly above it. So we are actually going to look at this problem instead. 8 to the 2/3. Now, if you're like, ew, fractional exponents, how are we even supposed to go about simplifying this? This is where we start getting into that last little piece we talked about yesterday, that when we see fractional exponents, it's actually a way of representing radicals or roots. Now, our strategy for simplifying this, and I know some of us have already started reaching for our calculators, we're going to see how we can do this without our calculator, and we call it splitting the power. No calculator. So what we want to do is break up this power into the root power, such as 1/2 or 1/3, because those give me a square root and a cube root, and then the other part of the power, which will give me what we are powering up that base by. So if I look at that denominator of that power, we see that we have 3. So I can break this up into the root power, 1/3, raised to the 2nd power. So using our math spam rules, is 8 to the 1/3 squared the same as 8 to the 2/3? Yes, because if we're powering up, we would multiply those exponents together. So where this gets us in simplifying is, we know that 8 to the 1/3 is the cube root of 8. So 8 to the 1st power divided by index. And what is the cube root of 8? 8 is a perfect cube, and its cube root is 2. Our last step, what is 2 squared? 4. And you could actually verify this on your calculator, that 8 to the 2/3 is indeed 4. All right, folks, that is it for page 1 of our notes. We'll go ahead and turn to the next page for our next video.